Yeah, thank you very much, Tanya. So I'm speaking about Nanorod, so I made the title longer instead. So thank you very much for the introduction, and thanks a lot, Professor Zimmermann, for the kind opportunity to speak here today. The nanorods I will speak about, they are derived from cellulose. They're so-called cellulose nanocrystals. I at least avoided that in the title to keep it shorter. They are interesting because they form liquid crystal phases. They are chiral, cellulose is chiral, so they form cholesteric liquid crystal phases. And the background image is in fact an example of the textures that you can see from them. And this is interesting for a physicist, that you get the spontaneous development of long-range order and also a helical modulation of that. But CNCs, as they're often abbreviated, actually attract a lot of attention today also from a general materials community. And I have to be honest, for them the liquid crystal formation and the physics is maybe not always the most important. So I'd like to start saying a little bit about why there is an interest in these materials. But in fact, it is, of course, related to the liquid crystal formation. But in principle, what makes people interested in these is that you can make functional materials from them, such as this film. This is basically paper, photonic crystal paper, if you like, that is prepared simply by taking a suspension of cellulose nanocrystals, putting a drop on a glass slide, and letting the water evaporate. And the colors you see are structural color, so the colors are there because of a periodic structure within the film that these nanocrystals have formed. And if you think about it, we are talking about nanoparticles, and we can prepare films of several square centimeters in this very, very easy way that have uniform properties, basically more or less uniform properties across the film. And that's quite remarkable. And the reason for this remarkable possibility is, of course, the fact that cellulose nanocrystals form these cholesteric liquid crystals. So, brief slide on what are cholesteric liquid crystals. It's a chiral nematic. The nematic says that the rods are aligned locally all in the same direction. We call that the director. And the chirality means that the director orientation is rotating in a helical manner as you go in the direction perpendicular to the director. And the interesting thing from the materials point of view, or from the applications point of view, is that the period, the pitch of this helix can be very short, on the order of a few hundred nanometers. And that means that you have a material that is periodic on the scale of visible light wavelengths, which means that you get Bragg scattering, as we know from X-ray scattering, but in this case for visible light. And you can easily see that by taking a cholesteric, looking at it and tilting it, and you see that the color, you see intense colors, and the color changes from the same sample just by tilting it from red to blue, because this color comes from the Bragg scattering. And you actually find a couple of examples in nature where nature uses this structural color. This is from Silvia Vignolini's group. She studied these berries that I don't remember what they're called anymore, but they're quite beautiful, and they have a strong, intense blue color from a helical arrangement of cellulose. And you find it also in the animal kingdom, of course. Quite a few beetles have structural color as well, again from, in this case, again from a helical arrangement, not of cellulose in this case, but of chitin. But the result is the same, even if the polymer is slightly different. And the chitin is also interesting, and the animal kingdom helical arrangement is interesting because it's not only colors that we can get from this, you can also get spectacular mechanical properties. So for instance, this here is a so-called mantis murder shrimp in the process of preparing its lunch. It has these clubs that it hits rather well-protected animals with. And the interesting thing here is that it's always the mantis murder shrimp that wins. Anyone who ate the crab knows that the crab shell isn't exactly weak. So the question one may ask is, why is it that the crab shell breaks and the clubs don't break? And David Kizelius and co-workers, a few years ago, they asked exactly this question. And so they investigated these clubs with a number of techniques. And they found that it's due to, again, the helical arrangement of chitin, but with an incredibly well organized helix with a graded pitch that really dissipates the force and prevents crack formation. It's really quite spectacular. So this example from nature can be a good inspiration also for artificial materials, because maybe you have heard that 3D printing is now going beyond the lab and really being seriously considered for manufacturing large-scale structures like even houses and cars and bridges. And a problem with that, as you can read in this Wired article, is that the 3D printing method we are using today, they make brittle structures. So if you try to subject these to the loads that a typical house may be subjected to, they will break. And of course, it's an interesting idea then if you can 3D print, for instance, cellulose nanocrystal suspensions, let the cholesteric liquid crystal formation do its magic and polymerize a flexible polymer within that, then you might be able to do very tough and lightweight 3D printed large-scale structures. So it's a quite interesting perspective. Now, so you can do a lot of things with these. So the next question is, of course, where do they come from? Well, cellulose is the most abundant polymer on Earth. You find them in every plant. So you can take, for instance, a tree. If you are a naughty person, you cut it down and you look at what is inside, and you will find that it has a tubular cellular structure. And if you look at what those tubes look like, if you look at the walls, you will find that they actually consist of several walls, and within each wall is a fibrillar structure. And those fibrilla are in turn made up of small filaments that are twisted. And in those filaments, we can distinguish amorphous as well as crystalline parts. This is now pure cellulose. There's nothing else. At this scale, there's only cellulose. But both amorphous and crystalline. But you can remove the amorphous parts by acid hydrolysis, and you then end up with these nanorods, which we call cellulose nanocrystals. They are on the order of 5 nanometers wide and a few hundred nanometers in length. And I mentioned that we use sulfuric acid hydrolysis. That is actually important because not only it's important because it makes the surfaces of the nanorods charge. It imposes sulfate half-ester groups. And this is nice because it makes the nanorods easy to disperse in water. But as you will see also, the surface charge and the counterions tend to be really important also for what the behavior of suspensions of these rods are doing. I should also say that in our case, we use commercial CNC, and there the proton counterions that were there after the acid hydrolysis have been exchanged for sodium. So that's nice, it simplifies the things for us a little bit. Now, what happens when you look at these suspensions as a function of concentration? So if you just have a little bit of these nanorods, you get an isotropic phase up to about 2-3%, depending on the source and how you process them. But then the liquid crystals phase starts forming around 5%, 4%, or something like that. If you continue increasing the concentration, liquid crystal scientists might think you're going to see a smectic or a columnar phase. Unfortunately, from that perspective, it doesn't happen because you always get kinetic arrest into a gel-like state. You turn the vial upside down and you see it doesn't flow anymore. And this gel is, in one sense, a nuisance because it prevents us from expanding the liquid crystal phase diagram. It reduces our ability to tune the cholesteric pitch and so on. But on the other hand, in another sense, it's actually a blessing because if it weren't for the gel state, you wouldn't be able to prepare these films. The gel state preserves the cholesteric helical arrangement that happens at 85 to 90% water, and that's why it's still there when we have evaporated the water completely. So that gel state is interesting in many respects, and the competition between the gelation and the liquid crystal formation is interesting. So the people who are trying to make applications with these, they have a couple of challenges, mainly related to getting rid of that gradient or that spectrum of color, making a uniform color, controlling the helix orientation and so on. But the interesting thing for us is that almost every of these challenges is connected to a very interesting challenge in terms of soft matter physics. So, for instance, what actually determines the phase diagram? If you change the CNC aspect ratio, if you change the surface charge density and so on, what happens? What determines the structural development? What determines the pitch you get? What determines the time with which the helix develops? And this out of equilibrium behavior, when the kinetic arrest sets in, when the gel sets in, what determines when that happens? And finally, of course, there's a lot of interest in droplet drying, and that's exactly what we are doing. And anyone who's looked into droplet drying of suspensions knows that there are a lot of things going on that are quite complicated. So there are really tons of interesting questions to investigate here, and we're working on all of them in our group. But for today, I just decided to focus on two, which are related, and that is the phase diagram versus the kinetic arrest. When do they happen? And they're related because the aspect ratio should influence both of them. The liquid crystal formation happens because, according to Onsager, nanorods, rod-shaped objects tend to align in the same direction to reduce the free energy, to maximize the entropy. The gelation happens because of percolation, and you need rods to be a certain length to find percolation at a small volume fraction. So there is an interesting conflict here, actually. And on the one hand, fractionating or increasing the aspect ratio should be good in terms of expanding the liquid crystal phase range, at least to promote liquid crystal formation. On the other hand, you also promote percolation, and you would expect a gelation at an earlier stage. So a question here is, can we, first of all, will this happen? Which of these will dominate? Can we expand the liquid crystal phase range in this way? Or maybe percolation sets in earlier and we even reduce it. We didn't know when we started with this. So that was one of our main questions that we wanted to answer. And the problem here is that CNC suspensions, when you start with them, they are notoriously disperse. There is a very large variation in rod length. So you cannot just say, I want a long rod sample and a short rod sample and compare them. You have to actually fractionate them. And the question is then, how do we go about to fractionate them? Well, here, liquid crystal formation of nanorods actually comes to our help. So I think this audience probably most know the Onsager model, suggesting or explaining why you have a nematic ordered phase happening beyond a certain volume fraction of rods. It depends on the aspect ratio, L over D, length over diameter, and you have two volume fractions. That's important for this. You have a lower volume fraction, which is the limit of the... is it mine? I think something is beeping. I don't know if it's... I don't know. Okay, anyway. Maybe. You have a lower volume fraction, which is phi equals 3.3 times d over L, where the isotropic phase becomes unstable, and you have a higher volume fraction where the nematic phase, if you go from above, becomes unstable. And what I will be doing quite a bit in this talk is to look at what happens as a function of a CNC fraction. And what we do then is we look at the volume fraction of nematic phase to isotropic phase, so that's our uppercase phi. And so if you plot the typical curve, you find that at low CNC fraction, everything is isotropic, so your uppercase phi will be 0, but at some point it will increase, and you get to 1 when you are past the second threshold. Now, the interesting thing, we are focusing here on the range of that is in between these two thresholds. I think it's mine that is doing this. I don't know what it's doing. Okay. Anyway, between these two thresholds, the phase coexistence regime. And the question is then what happens there? So what happens there is that the nematic phase starts forming as droplets or tactoids, as they are called. And importantly, they have the higher volume fraction of CNC. And since cellulose has a higher density of than water, these will then fall, eventually sediment and form a lower phase. And this actually happens. So this is what we see when we look at these samples between cross polarizers, that the liquid crystal phase sediments to the bottom. And this is nice because we can separate these two phases and look at them separately. And the reason that this is interesting is that the threshold for liquid crystal formation is proportional to L over D, the aspect ratio. So if you have a polydispersed system, if you have a local fluctuation in aspect ratio, that then a certain volume with larger aspect ratio will first form the liquid crystal phase. So these liquid crystal forming tactoids, they will have a larger aspect ratio. And the others will have a lower aspect ratio. And this works, it's actually been known for some time, but if you just do this once, you won't see any effect. So Camila devised a pretty nice protocol where she did this repeatedly. So she separated the two fractions, and then she diluted the high concentration until she got to the phase coexistence regime again, and she evaporated water from the low concentration until she got in the phase coexistence regime again. And then she repeated the process 3 times. And 3 times was in fact sufficient to really see a difference. And she then in the following I will compare the III sample, which is 3 times isotropic fraction, and the AAA sample, which is 3 times anisotropic fraction. And if you look at the AFM images, you see quite clearly, I think, that these are the same. They are the same scale. So you see, I think, immediately that the AAA sample really has much longer rods than the III sample. And to quantify it a little bit, here are the statistics. The original sample has an average aspect ratio of 57. The AAA fraction, it goes up to 61, and the III fraction, it goes down to about 46. So this was nice. We managed to get these different aspect ratio and fractionated samples. So then the question was, of course, what would we see? And our expectation was that, well, compared to the unfractionated sample, we should be seeing the isotropic nematic transition to take place at lower CNC content for the AAA sample, but we expected that also the kinetic arrest should take place at lower CNC content. So we didn't know if we would see an expansion of the phase diagram. And what did we see? We saw the following. This is between cross polarizers. We have a lot of vials with different concentration. The top row is the initial suspension, the second row is the III, and the third row is the AAA. And the liquid crystal phase is revealed because it's bright. And what you see is that we actually have a really nice expansion of the phase diagram. We reduce the onset of liquid crystallinity to just above 3% from 5% to begin with. And that's really nice. And what is also very nice is that we have a fully liquid crystalline sample at only just about 6.6%. And that's important because in the original one, the fully liquid crystalline phase happened only at about 10 or 11. And that's the same concentration as where gelation sets in. You can in fact see gelation also because you see this meniscus starts getting distorted because it's no longer in equilibrium. And if you use that, you can already in this picture see that that expected change in kinetic arrest doesn't seem to happen. The distorted meniscus happens at about the same concentration in all 3 samples. So to better investigate the gelation, we flip the vials upside down and we look whether they flow, and we see that indeed it's only the high concentration samples at 12 and 13% that are gelled. All the others they flow. And that really surprised us. It seems that gelation is totally unaffected by fractionating the sample. So we asked ourselves, of course, well, first of all, this is great because we have really expanded the equilibrium phase range of the liquid crystal phase, but we asked ourselves what could then be the reason for the gelation if it isn't the aspect ratio. And what we realized is that, well, there is one thing that is changing very consistently in all these 3 samples, and that is, of course, the amount of counterions, because whether they are long or they are short, it's the same CNC mass fraction and there is the same surface charge density on all of them. So it seems to have something to do with the counterion concentration. And to check this, we then thought, okay, let's see if we can induce gelation also at lower concentration of CNC by simply adding salt, sodium chloride, until we have the same ionic strength as in the samples that we know gelate from before. And that concentration we estimated. It's difficult to estimate because also the values of surface charge from the manufacturer are not completely reliable, but we estimate at about 39 millimolar sodium counterions, that's where we should expect gelation. So then we didn't care anymore about 12 and 13% because we just wanted to look if we could induce gelation at lower concentrations. And then we added sodium chloride up to 39 millimolar concentration. And at first, the result is disappointing. None of them is gelated, they all flow down when we turn over the samples. But remember, this was just an estimate, and it was not very high accuracy. So we continued, we added up to 43 millimolar, and you see now things are changing, and at 45 millimolar, everything beyond higher than 2% CNC is gelled. So in fact, it seems by tuning the counterion concentration, we can really control gelation. And moreover, if you look at the samples between cross-polarizers, the previous ones were without polarizers, then you can also see where something forms a liquid crystal. And that surprised us as well, because they all are liquid crystalline. Even the 2% sample that is not gelled forms a liquid crystal. So that suggests to us that somehow the effective rod length seems to be increasing by adding counterions. And the question is, of course, how? So I'll come back to that question in a moment, but first, just regarding the question of whether the kinetic arrest is gelation or not, that was an important issue in the beginning, at least. So we did rheological investigations as well. And here is the modulus. This is the storage modulus. This is the loss modulus as a function of shear rate of the sample holder. And if you look at 4% no salt, this is actually isotropic. It flows perfectly well. We have a typical liquid behavior where G prime, the storage modulus, is much lower than G double prime. If you go up to 9%, of course, both moduli go up, but you still have the black dots, the storage modulus being below the loss modulus. And indeed, 9% is not gelled. But at 13%, we know that this one is kinetically arrested, and there the situation is reversed. So this is the typical fingerprint of gelation, if you like, so that seems to be a pretty good confirmation. And then, of course, an interesting question is what happens with salt. So we look at the 4% sample again, but now with salt up to gelation threshold, and indeed the G double prime is lower than G prime, and of course the same thing for 9%. So this all makes sense. So back to the question of, are the rods getting larger by counterion addition? So we took 2 weight percent samples. They are well below liquid crystal formation. They flow very easily. And we looked at AFM at the rods. And the sample suspension without any salt looked like this at AFM. That's our starting sample. And when we add 20 millimolar NaCl, we see that indeed the rods actually appear to be extended effectively. And at 40 millimolar, you really see much, much larger rods, even a bit of network formation going on. So this seems to support this idea. So it seems that the individual CNCs are still, they have a high enough aspect ratio to form liquid crystals, but it's still far too low to percolate at the concentrations we are dealing with here. But if we add counterions, we get an aggregation of CNCs to effectively get larger, higher aspect ratio to the extent that we even reach the percolation threshold. And the question is then, of course, why do we get this apparently end-to-end, more or less linear aggregation? And that's not easy to answer at all. And we had a visit by my old friend from my PhD time, Mikhail, and we described our results to him, and he had an interesting idea, and I point out a modest proposal here, because we are by no means saying that this is the true explanation, but it's the only attempt of explanation that I've heard so far, at least. So at least we are considering it. And the idea is basically that where gelation is happening, we are still in a regime, in a DLBO regime, if you like, where you have a barrier against aggregation, but it is weak. It's on the order of KT. So if you would have a slight fluctuation, that could temporarily bring down the barrier to such an extent that the nanorods may aggregate. And once that happens, of course, that's permanent, or at least until you do something mechanically to it. And the question is then, why would this happen? And Mikhail's point was that along the CNC, because it's such a long rod and a lot of surface, a local fluctuation will have very little importance. because it won't really change the interaction between these large surfaces that are in contact. But at the ends, it's a very small surface area. So even a local fluctuation of counterions might in fact temporarily induce an attractive situation where, for instance, a sudden increase in counterions between two rod ends might lead to a chain formation. And once they aggregate, they would stay aggregated, and that would be a possible explanation. So, to summarize, at the end of my talk, what we have achieved is we can fractionate CNC suspensions, that's quite nice, according to aspect ratio, by separating isotropic and anisotropic fractions multiple times. We've done it 3 times. We can probably do even better by continuing this. The higher aspect ratio suspensions, they have a larger equilibrium liquid crystal phase range. Interestingly, now we can go over several % without having kinetic arrest and still have complete liquid crystallinity. We couldn't do that before. Gelation happens for all the different series at the same fraction of CNC, which was a big surprise to us, and in fact at the same counterion concentration. And we are quite confident that the experiments confirm that we have end-to-end aggregation more or less. I'm not saying just end-to-end, of course, but we have an effective lengthening of the rods at high salt content, and perhaps the repulsive barrier might be reduced at the rod ends in order to explain this situation. But that's a very open question, and I would be very happy, especially for the last point, if anyone has any other suggestions. So thank you very much for your attention. If you have any questions, I'd be very happy to answer.